Hello. My name is Ignacio Palau Rivera. I'm a program manager for the Rapid Manufacturing Institute, and I want to welcome Professor Robert Brown to the 2018 ASCHE Spring Meeting here in Orlando. Professor Robert Brown is the director of the Bioeconomy Institute at Iowa State University. Professor Brown, can you tell us a little bit about your current project with Rapid and some highlights about some of the process intensification aspects in it?
Very good, Ignacio. As you know, I'm an advanced biofuels guy, and I'm always interested in ways we can take biomass and convert it into renewable fuels or bio-based chemicals. One of the things that we do is we use a process called pyrolysis. It's a thermal process. It needs energy to run it. Normally this is done by figuring out how to transfer heat into the reactor. Heat is something that is fairly inexpensive, but it turns out it's fairly hard to get into a reactor. It's a surface area phenomenon, whereas the pyrolysis process itself is a volumetric process. Think of an automobile engine. You buy an engine based on its volume, its liters, and yet if we need to get heat into a reactor, it's based on the surface area, square meters, square centimeters. What we've come up with is the notion that we could improve the pyrolysis process by eliminating heat transfer altogether and coming up with chemical reactions that are exothermic, going to release heat into the reactor. It turns out to be fairly simple to do. We bleed a little oxygen or air actually into the reactor. It does something we call partial oxidation. We're not even sure which molecules are being consumed, but there are some. And we release enough heat that actually will drive these endothermic heat absorbing reactions that drive pyrolysis. Turns out it's a very small amount of air to do that. Turns out it doesn't affect the oils that are a primary product from pyrolysis. And so it's worked out very well for us.
I know that you're thinking of extending that approach to other systems. Can you tell us a little bit about what you're thinking of doing next or possible extensions to it?
Well, we refer to this matching of an energy absorbing reaction with an energy releasing reaction as an autothermal process. Pyrolysis turns out to be a very good example. I asked students, what else could we deal with that is an energy absorbing reaction? It turns out there's a lot of examples from industry that range anywhere from drying materials to the petroleum industry that does a lot of processes. An example is cracking of petroleum molecules into smaller molecules. This is a highly endothermic process. It occurs at high temperature, and we have a reactor that we think we can test those ideas out. But first I asked a student to simply build a fairly simple model to see if it worked. And in fact, bleeding in again a very small amount of oxygen, we found that we could actually consume, in this case, some of the reactants that would provide the energy to crack the molecules into very valuable small molecules. These are going to be olefin molecules that are used for production of polymers, for example, in the petrochemical industry. The models say it works. And what's interesting is we're not sure why it works in pyrolysis, and we understand why it would work in cracking. The petroleum molecules are a lot simpler, actually, than the pyrolysis products that we're dealing with. We feel that this is going to give us an opportunity to apply it to other industries. And one of the reasons this turns out to be so important is if you want to scale up to an industrial scale, if you think, I tell my students, why is a mouse furry and an elephant not furry? It has to do with surface area to volume ratio. The bigger the animal is, the harder it is for them to lose heat, and so they don't need fur to provide insulation. Same thing as we scale up these reactors, our surface area to volume ratio gets smaller, gets harder and harder to get heat in. If we can eliminate heat transfer, we get these incredible enhancements in the throughput that we can of a reactor of a given size, and the cost goes down. The example I like to give is we are designing a pyrolysis reactor to process 50 tons per hour of biomass, which is a lot of biomass, in a reactor that's 36 inches in diameter. And a normal reactor would be much larger than that to accommodate the ability to get enough energy into the process to support pyrolysis at that scale.
Very good. Now I wanted to ask you about some of your other activities with the Rapid Institute. You've been a member for a long time. You're one of the initial founding members in Iowa State. You've had a project. You do other activities. Can you tell us a little bit about some of the benefits you derive from the connections to other members and membership in
Well,
general.
we're real proud to be a founding member, and that meant we came to the first meeting where that was talk about, could we form something called the Rapid Institute. I was real excited about it because we were starting to explore some ideas in intensification. We were working with some companies on modular manufacturing, and it turned out that was the mission envisioned for the Rapid Institute. How this has helped us is we already had commercialization partners to move our work in the pyrolysis forward to build this 50-ton per day unit. What we were missing was the pilot scale data to allow the company to be able to scale up to these demonstration scale and ultimately commercial scale. And so the Rapid Institute has provided us the funds to do the pilot scale work. It's laboratory work done at a scale that's, I'm going to say, on the order of a few kilograms per hour, and use that information to scale up and design a commercial scale unit.
Very good, thank you. I wanted to thank you, Professor Brown, for joining us here in Orlando and for all he does in his commitment to the Rapid Institute.